Welcome to Networks Professionals.
Welcome back, everyone. Let's jump right in. Today, we're doing an explainer on the fundamental architecture of the modern internet, the three pillars of IPv6 routing. We're going to cut through the legacy noise and break down exactly how IPv6 efficiently routes traffic all over the globe, getting right to the underlying logic of modern network communication. Let's do it. There's a really clear dividing line between networking eras. On the legacy side, you've got the heavy congestion of old IPv4 networks. Specifically, its total reliance on broadcast communication. Think about it. In the IPv4 era, if a device needed to find a service, it literally shouted out a packet to every single device on the local network. Every computer, printer, server, they all had to drop what they were doing, process that packet at the CPU level, and figure out, hey, is this actually for me? In massive environments, that constant background noise caused severe congestion and wasted so much computational power. On the flip side, we have the streamlined efficiency of IPv6. It completely throws out that chaotic broadcast method in favor of multicast. No more shouting, devices use targeted delivery now, and honestly, it's a massive paradigm shift in network design.
Okay, here is our roadmap for this explainer. 1. The death of broadcast. 2. Unicast, which is one-to-one. 3. Multicast, or one-to-many. 4. Anycast, one-to-nearest. And 5. What comes next? All right, part 1, the death of broadcast. Moving right along to part 2, Unicast, or one-to-one communication. So, Unicast. This is absolutely the foundation of direct communication on the internet. By definition, a unicast delivery system means that when you send a packet, it is delivered exclusively to a single, highly specific interface on a single device. It's like having a direct private phone line. Whether you've got a developer spinning up a secure SSH tunnel to a remote server, or just an end user downloading a confidential file, that data stream is totally locked in from point A to point B. No crosstalk, no flooding the network, and definitely no random neighbors snooping on those packets. It's targeted, it's precise, it's secure, and it makes up the vast majority of standard internet traffic you see every day. Now, if we break down the unicast category, you'll see it reveals a very logical hierarchy based on routability. Basically, how far is a packet allowed to travel across network boundaries? Right at the top, we have global unicast addresses, or GUAs. These start with the prefix 2000:3. These are globally routable across the entire public internet. They function exactly like your public IPv4 addresses. Down a level, we've got unique local addresses, or ULAs, starting at FC00:7. Think of these like your private IPv4 addresses. They're strictly for internal communication within an organization, keeping all that sensitive internal infrastructure securely off the public routing tables. And finally, there are link local addresses, starting with FE80:10. Now, these stay entirely locked to a single local network segment. They are strictly non-routable, but here's the kicker. Every single IPv6 interface must have a link local address to do things like discover neighbor devices and set up local routing protocol relationships. Also within the unicast family, there is one very specific sequence you absolutely need to commit to memory: :1/128. This is the IPv6 loopback address. It serves a vital diagnostic function, essentially letting a device send network traffic directly back to itself without ever pushing that data out onto a physical network cable. When an engineer is setting up a new web server, database, or app locally, they connect to this exact address just to verify that the system's own internal TCP/IP stack is working properly. It's a perfectly self-contained, one-to-one loop entirely within the host machine. Okay, Section 3, Multicast, or one-to-many communication. Now, Multicast is our one-to-many delivery system, and it was designed specifically to cleanly replace those outdated broadcast methods we talked about earlier. Instead of forcing traffic onto literally every device, Multicast targets a dynamic group of interfaces, and those are usually spread across completely different physical nodes. Devices actively subscribe to these multicast groups if they actually need the info, and they completely ignore the traffic if they don't. It's brilliant. This quiet, targeted delivery mechanism is exactly why the chaotic broadcast storms of the IPv4 days are entirely eliminated in IPv6 architectures. A single packet is sent out, and the network infrastructure efficiently duplicates it only down the specific paths where subscribed listeners actually exist. Talk about saving immense amounts of bandwidth and endpoint CPU cycles. If you take away just one core metric about multicast from this explainer, let it be this. All IPv6 multicast addresses, without exception, start with FF00:8. The second you see that double F in a packet capture or a routing table,
Boom, you instantly know you are looking at one-to-many multicast traffic. Having this massive, dedicated block specifically for group communication makes analyzing and filtering network traffic incredibly straightforward for engineers. To really grasp why this is so powerful, just look at how granularly we can target precise groups within that multicast space. If a device sends a packet to FF:1, it targets all nodes on that specific local segment, guaranteeing every IPv6 device receives it. But, and here's where it gets cool, if a routing protocol needs to share an update, it doesn't want to bother all the laptops and printers. Instead, it sends the update to FF:2. That packet explicitly reaches only the active routers on the segment. The endpoints never even see it. This highly targeted approach is the real secret behind IPv6's incredible efficiency on the local wire. Let's look at Section 4, Anycast, our one-to-nearest delivery. Anycast is such a clever concept. It is uniquely designed for one-to-nearest delivery. In this setup, multiple identical interfaces across entirely different physical nodes or servers around the world are assigned the exact same IP address. I know, it sounds crazy, but when a user sends a request to that address, the network doesn't just blast it to all of them. Instead, it relies on underlying routing protocol metrics, things like BGP path length or OSPF cost, to calculate which interface is topologically the closest. The packet is then seamlessly routed only to that single nearest node. It is a super powerful concept that basically abstracts geographic distance into pure network logic. The practical applications of routing traffic to the nearest topological node are huge, especially for heavy-duty enterprise load balancing and global redundancy. The premier real-world application of this, the global DNS root server network. By assigning the exact same Anycast address to DNS servers distributed all over the planet, an end user's web request is automatically directed to the nearest operational data center. This architecture is what keeps the internet lightning fast. Plus, it offers innate resilience. Think about it. If a specific data center experiences a total power failure or a major fiber cut, the routing protocol instantly updates its metrics. Subsequent user traffic seamlessly flows to the next closest operational server without any manual failover intervention required at all. But wait, here is a surprising technical twist that actually trips up a lot of networking students. Anycast and Unicast addresses are structurally indistinguishable from one another. While multicast traffic immediately stands out with that dedicated double F prefix we talked about, Anycast addresses are drawn straight out of the standard Unicast address space. There is literally no special sequence of characters that identifies an IP as an Anycast address. It's entirely a function of infrastructure configuration. A network administrator simply configures the routers to understand that a specific Unicast address is now being shared across multiple devices, which effectively grants that address dynamic, one-to-nearest superpowers. Finally, Section 5. What comes next? So we have comprehensively explored the fundamental architecture here. Unicast for precise direct connections, Multicast for efficient group delivery, and Anycast for resilient topological routing. But grasping the architectural theory is really just the beginning of your journey. So I'll leave you with this final thought to explore on your own. Now that you understand these three pillars, what's your next move? Are you ready to get your hands dirty and configure these addresses directly in an operating system? Or do you want to dive deeper into the complex subnetting concepts used for slicing up those global Unicast blocks? The foundational logic is rock solid. Where you build next is entirely up to you. Thanks for joining me for this explainer, and as always, keep learning.
Thanks for watching.